Hello. Okay, so now we are focusing on chapter 2, which is the modeling of discrete change. Okay, so basically we start to look at the dynamic system actually, all right? So I use this slot. I separate this slot into three category. Okay, I put it in a part one, where we are talking about more on the dynamical system in general term, and then part two, we start to focus on the difference equation. Okay, that is when we start to look how to adjust a little bit the difference equation. And then part three, we will start to look at the system. Dynamic system, which is linear in its original underlying fundamentals. All right. So we see how it goes then. Okay, first things first. Dynamic system. What is it? Okay, so if you have a dynamic system, this system is focusing more on changes. Okay, changes that you see in a situation. Okay, where your change now is. You measure the change over time. Okay, but you need to have a set of fixed rules. Okay, so meaning that how you can actually determine one state of a system. You look at the difference between one state of a system right now and this state of a system in the next state. All right, so meaning that just bear in mind, when you have a dynamic system, you have two set of sets, for example. But in the next once you understand this two state system, then we can proceed into whatever happened in a long run and state system. Okay, but this particular state, we call this a phase space. Okay, a phase space. Okay, so this phase space is very important in dynamical systems. All right, so how you're going to understand the phase space? Okay, this is a space where you can put all your sets of function. Okay, you can describe a change in the system over time by using this the phase space. All right, so more or less you can imagine, one, you have the dynamical system, meaning that this is something, the evolution of the system, you can see this. Okay, the evolution of a system, you can see it over time. Okay, so the simplest example is a bacteria. Okay, because you know bacteria, it double in size, it double in species, right? For example, you have one bacteria, and then this bacteria, the chromosome of the bacteria double. Okay, double meaning that it has similar genetic properties, and then it move into the next step, which is two organisms, similar organism. One and then it separate into two individual organism, and you can foresee that from these two entities, then now it will become double from two into four, and so on. Okay, depend if let's say we don't have any additional distraction, okay, or disruption that disrupt the evolution of this species. All right, so this is the example of the dynamical system. Okay, why this is the main example? All right, because you can see from here. Okay, I jot down here a little bit. Okay, you have one entity over here, and then it moved into two different entity over here, and then you can imagine this is your phase one. Okay, for example, I just give you idea first, and then this is your phase two, right? Okay, so this is the concept of phase state. Okay, so you have actually the state one, and this one is state two. Okay, state one and state two. Okay, let me remind you of this. All right, if you notice about the state, Normally people will say that dynamic system, the evolution of a dynamic system can be sustained or can be identified through time. Okay, that is correct. Okay, as long as your evolution comes through time, that is correct. But in this sense, the bacteria, we are not talking about the day one, day two, and so on. Okay, in this case, we are talking about the time where the separation starts. All right, meaning that from one until two. Okay, state one and state two doesn't mean that your day is one and state two is day two. No, okay, it means that in what day this particular separation occur. Okay, so that is why we are using state phase. Okay, so that is why we don't use day one and day two. But if let's say you are able to calculate this kind of separation in a day, all right, meaning that day one you have certain days, and day two suddenly you have a consistent behavior where in day two your bacteria double, day three your bacteria double again. Okay, that is um too good to be true. But if let's say you have that, then that's fine. You can identify your state as in a matter of your day. All right, so that is a part of the example. But whatever it is, you have to really identify what is the phase state in your own case. Okay, so every case is different. All right, so that is the interesting part about dynamical system. Okay, um, so they give you example like this. Okay, for example, like you identify. Okay, assume you assume that we are dealing in idealistic ways. Okay, let's say the population, all right, it will double according to the time step it takes is consistent. Okay, meaning that if let's say it double in the organism double in one day, the next step your organism double also in one day. All right, it is may not necessarily so, but to make it simple for us to study, so we assume that. All right, so in this case whatever happened, okay, since every bacteria, okay, divides into two during each time steps, okay, so we can approximate a little bit the population size at the next step. Okay, so for example, if our first BN, okay, we start off BN, our BN plus one, BN plus one meaning that the next steps ahead of time, one step ahead. Okay, one step ahead, not two, not three, but one step ahead. It must be two times the previous population, right? So basically, we can just simply safely say that my bn plus 1 must be equal to must be equal to 2 times bn. All right, it makes sense, right? Because it double inside. Sorry, it double in quantity of the organism, so it must have the similar formulation, mathematical formulation. So in this case, my function for bn is equal to to bn over here. Okay, that's why you have this. All right, that's where you have this. Okay, so that's the concept of it. And then now, okay, since we are dealing with a dynamic system, we need to have the first prior state. Okay, so we call that initial points or initial states. All right, so in this case, for example, you have the rule. Okay, right now your rule is just bn plus 1 equal to 2 bn. And then you now deal with the initial, in this case, population. Okay, initial population size. So in this case, your b naught. Okay, b naught over here, meaning that at t naught, okay, assuming your t naught, you start with the first population size. Okay, so these two goes together. That's how you're going to develop your dynamical system. All right, so when we call dynamical system is well defined, okay, it means that first you have the phase state. Your phase state is already established. Okay, in this case, your phase stage in a form of function. and then your function is also established. Okay, so your function and your phase state is established. Okay, so in this case, you have one rule that utilize your function, and then you already identify what is your phase state. Okay, your phase state meaning that the time it doubles consistently, and also you already identify your initial b naught. All right, so by the end of the day, your dynamical system is already well defined. Okay, this is what I said earlier. You need to have a state space earlier, and then you need to have a function, which whatever it is, it will tell you um, how your system will behave. Given that you already know what is going on right now, how your system will behave in the next future, in the next one step at a time, in the future. In the previous case, you are able to, if let's say you know your current situation right now, you already have 10,000 uh, bacteria. Okay, and then you know the next stage it will behave in double, meaning that, oh, the next step of the generation I will have 20,000. It's as simple as that. Okay, but normally I would like to emphasize dynamical system is not that straightforward like this. Okay, it involves with a lot of different system that you need to consider, and how to define the function, that one is a little bit tricky, and that one is a little bit needs more um investigation. All right, okay, and how you're going to reflect that into a calculation, especially on numerical calculation, that one is also quite tricky. Okay, because you need to know the stability of the system, the stability, the sensitivity of the original system, and whether your system reach the equilibrium solution, or whether your system will not get any solution. And if let's say you don't have any solution, what would you do next? Okay, so that is what makes it a little bit tricky, and a little bit complicated by the end of the day. All right, but generally we will try to give you a little bit of some general information on how you're going to model certain particular problem that involve with dynamical system. Okay, so I'll see you in the next part.